So to conclude that last problem we did, using technology, the chi-squared test statistic comes out to be 3.06, and the p-value comes out to be 0.08. So let me write that down up here. The chi-squared test statistic was 3.06, and the p-value was 0.08. And so with a p-value of 0.08, you would not reject your null hypothesis. And so there's no reason to think that this distribution is different than our expectations. So here's how you would write that conclusion in APA format. The general format is you write your conclusion in a sentence. You let the reader know that you used a chi-squared test analysis. Then you put in the degrees of freedom. You record your test statistic. And then your p-value is always compared to 0.05 or 0.01 if you have very strong evidence against your null hypothesis. So this is how we would wrap up that problem. We might write, a chi-squared goodness of fit test showed that the frequency of dream recall during REM sleep was similar to what was expected. Our chi-squared test statistic was 3.06 with 2 degrees of freedom, and our p-value was greater than 0.05. Okay? All right, so the next kind of chi-squared test that we'll talk about is the chi-squared test for independence. And the central question that it answers is there an association between two categorical variables? Another way of putting that is, are these variables independent or are they dependent? So here's an example. Is there an association between serotonin levels, low and high, and depression? Yes or no? Here's another example. Is there an association between cola preference, Coke or Pepsi, and depression? Yes or no? So you can see that these levels of measurement are at the nominal level, and that's why we're approaching this with a non-parametric method. Okay, so this is a picture from your textbook, all right, about the idea behind a dependent relationship and an independent relationship. So for example, if preference for cola and depression have no association at all, then this might be the type of data we would expect. If we had 100 subjects, we'd expect about half of them to be depressed, half of them not to be depressed, about half of them to like Coke, and about half of them to like Pepsi. However, if we saw data that looked like this, where the numbers were clearly not equal, we might say, it seems like there's an association between these variables. In other words, one variable might be dependent on the other, okay? And so we can see that the frequencies in the first example vary across the table, whereas those in the second example do not. This is a true case that was data that was used, where a chi-square test for independence was used to establish whether or not there was gender discrimination going on in the workplace. And this is a common place that you might see this test applied. So here was the scenario. 48 male bank supervisors were given a personnel file and asked if the person should be promoted. The files were identical, except the supervisors were shown files with male applicants and the other half were shown files with female applicants. So this should say half the supervisors were shown files with male names, half of the supervisors were shown files with traditionally female names. And of the 48 files reviewed, 35 were promoted. Okay, so what would it look like if there was no discrimination? So remember, 35 were promoted. So if there was no discrimination, about half should be male and half should be female. So let's just say half of 35 is 17-ish. So maybe we have 17 males promoted and 18 females promoted, or something like that. 13 were not promoted, all right? So again, we would want that to be about half and half. So there were 48, so there were 24 of one and 24 of the other. So for example, there would be 6 here and 7 here. So roughly half and half. So this is what it would look like if there was no discrimination going on, or something close to that. What would it look like if there was discrimination? So remember, there's only 24 in this category and 24 in this category. Otherwise, it might be tempting to write 35 here and 0 here. But remember, there's not that many in your set that you're looking at. Okay, so what might discrimination look like? Well, maybe, well, this is obvious, right? All of the males and none of the females. Oh, wait, there's 35 promotions. We can't do that. So all of the males get promoted and none of them are not promoted. That would mean that there would be room for 11 females to be promoted, and that would mean that 13 were not promoted. So this would be an example of clear discrimination when all the people not promoted were female and all of the males would get promoted. All right. But you can see that there's a lot of wiggle room between this first chart and this second chart. Like, what if this was 20? You know, how can we tell whether or not discrimination is going on? Well, this was the actual data from the study. And so the question is, do we think that there's evidence of discrimination, or could this result have happened purely by chance, that there's no relationship or no association between gender of applicant and promotion status? All right. So again, the hypotheses in these tests are written out in sentences. So we could write, there's no association between gender and promotion. That would be our null hypothesis. And our alternative then would be there is an association. Now, it depends on your preference. If the word association makes sense to you and you understand what that means, then that might be how you choose to write your hypotheses. If it's easier for you to think about variables being independent or not independent, you might write them this way. Gender and promotion are independent, and the alternative would be gender and promotion are not independent. So again, the null hypothesis is always there's nothing going on, status quo. There's no association between these variables. These variables are independent. The alternative is the opposite of that. There is an association between these variables. These variables are not independent. In step number 2, the assumptions. The assumption in this test is that all the expected counts have to be greater than 5. That's the big assumption. And then, of course, that your sampling was done well. The sampling was random and independent. Now, how do you find the expected value for each of the cells in your data table? It's the row total multiplied by the column total divided by the grand total. Okay, so yay technology. Technology does this for us. So when I put this data into statistical software and analyzed it, so I put in all of this data into the table. And again, just to be clear, this is your data right here. These totals are simply helpful if you were going to do some calculations by hand, but those aren't part of your data. Okay, so I fed the data into a statistical software program. And when I did, my test statistic came out to be 5.17 and a p-value of 0.02. And with a p-value of 0.02, we would be rejecting our null hypothesis. So again, we would say, if these are our hypotheses, we reject this. There is an association between gender and promotion. Or if you're using this other set, we reject this. Gender and promotion are not independent. Okay, so here's our informal conclusion. There is an association between gender and promotion. And here would be our conclusion in APA format. A chi-square test for independence showed a significant relationship between gender and promotion status. Again, chi-squared letting your reader know that you approached this with a chi-square distribution. The degrees of freedom in this case would be equal to 1. Here's our chi-squared test statistic, and our p-value is less than 0.05. And then here's a clarifying sentence. The data indicate that males are more likely to be promoted in this organization than females. Okay, so let's talk about the expected value. I just want to show you how an expected value of a cell is calculated. So I'll do the expected value for this cell. All right, so the expected counts, it's the row total times the column total divided by the grand total. So that's why sometimes you'll see these tables written with totals. So the row total would be 24. So it's the row total times the column total. So the column total is 35 divided by the grand total. And the grand total is the total population that you were, the total sample size. And so if we were to do that, that would be 24 times 35 divided by 48. And that comes out to be 17.5. And you would have to do this for each of the cells in your table to make sure that all of these expected counts were greater than 5. If the expected counts were not greater than 5, then you need to use another non-parametric method, which we're going to be covering in our last class where we cover new material in a few weeks. Okay, so that's the chi-squared test for independence.